All right, so we started from the ocean now to the roads, and now let's get to the air. So our next speaker is Dr. Richard Garcia. He's a senior research engineer at the Southwest Research Institute. And Dr. Garcia has over 10 years of experience in designing all forms of autonomous unmanned systems, including ground and aerial vehicles. So he's going to talk about how do you explore damaged nuclear power plants with unmanned aerial systems. And if you don't know, actually, University of Virginia has a decommissioned nuclear power plant on grounds as well. So, maybe we can use some of this. It's been very clean. Correct. So.
It's the cleanest place in the whole colony.
All right. So with that, I'll hand it over to Richard. Yeah.
Thank you so much. Oh, well, thank you for everybody attending. I will try to keep this to 15 minutes to maybe get closer to schedule. I'm here to talk about exploring damaged nuclear power plants using small unmanned aerial vehicles. And as most of you probably remember, on March 11th, 2011, a devastating earthquake occurred off the coast of Japan. And it damaged roadways, buildings, critical infrastructure. And to give you an idea of the sheer magnitude of the earthquake, it's estimated to have shifted the island of Japan 8 feet to the east, and it's estimated to have shifted the Earth's axis by 4 to 10 inches. In addition to the earthquake, it triggered a tsunami. That tsunami devastated the coast of Japan. All told, over 15,000 people lost their lives, over 6,000 people were injured, and over 300,000 people were displaced from their homes. And as you probably also remember, the Fukushima Daiichi nuclear power plant was one of those pieces of critical infrastructure that was damaged during both the earthquake and the tsunami. Unfortunately, the 1-2 punch of both the earthquake and the tsunami caused the loss of both primary and backup power, which caused loss of cooling to reactors 1, 2, and 3, which caused the fuel to melt and then escape the pressure vessel. And you'll see this in this small animation here. The top right images gives you an idea of what this area right here looked like prior to the meltdown, and the bottom right is what it looks like right now. So move ahead 8 years where we are today, and there are still areas of units 1, 2, and 3 that we have little or no information about, which are still critical to the decontamination and decommissioning of those sites. And one of the direct questions is kind of, well, why are we still missing information 8 years later? It's an extremely challenging environment to work in. First and foremost, it's highly radioactive. And I want to give you a scale of what I mean by highly radioactive. A US worker working in the radiation field can legally accept 0.05 sieverts of radiation cumulative over an entire year. The estimated values inside of the pedestal area, which is this central area here, inside of Unit 2 is 1,000 sieverts per hour. So just to give you a scale of what we're talking about. It is a very confined space. I've been in Unit 5 myself. You're actually squeezing between pieces of equipment. It's dark. So this area here is the primary containment vessel, the pedestal, and that itself is inside a building. So it's a building and a building and a building. So it's completely dark. It's pitch black. There's dripping water in this environment. And that's because they're actively pumping water into these units in an attempt to keep the melted fuel underwater. It's foggy, as you can actually see in the previous investigation videos by some ground vehicles on the far right. It's a small access point, which I'll talk a little bit more about further on in the slides. But just getting into the primary containment vessel in an effort to get into the pedestal to actually see the melted fuel, you have a very, very small entry point. And then last, it's a damaged and unknown infrastructure. Of course, we knew what it looked like before, but it suffered a tsunami, it suffered an earthquake. Grates have shifted, things have fallen on the floor. Additionally, now there's old robots that have been put in and died in place. There's old tethers, all of that is now in the way, making this an even more complicated environment. So having said all that, TIPCO Holdings approached Southwest Research Institute, which is where I'm from, and the University of Pennsylvania, and they wanted to know, hey, is there any way that a small unmanned air vehicle could actually function inside of the primary containment vessel, get to some of these locations where we don't currently have information and collect that data for us? And kind of the rationale behind that is, First and foremost, there's a lot of stuff on the ground. The ground is a very complicated environment to work in general. But then you add in all the tethers, all the dead robots, all of that, it becomes even more difficult. Robots have been stuck between grading that had shifted. It's a difficult environment. It also takes a long time. Some of the ground vehicle explorations have taken hours and even days, where an air vehicle is estimated to be able to do it on the order of minutes. So as you can imagine, there are a lot of components to this type of problem. The first one I want to mention is the platform modification. You need a platform that's going to survive in this environment. First, it needs to fit into the environment. Then it needs to be able to survive the radiation, it needs to be able to survive the humidity, the rain. Additionally, it needs to be autonomous. Unfortunately for us, we can't carry a tether through our mission. We also can't guarantee wireless communication for the entirety of the mission, which as such means the vehicle's going to have to be autonomous, which means it's got to do path planning, it's got to do localization, it's got to do obstacle avoidance, all of it on board. Additionally, we have things like simulation. Obviously, we can't create a test fixture that mimics all of what's happening at Fukushima Daiichi. It's just impractical. We do actually have a scale 1-to-1 fixture that we do testing in, but we can't make all of it raining. We can't make all of it radioactive, especially at these levels. So we had to do small pieces of testing and then extract data from that and then do a lot of simulation just to further our development and design much, much faster. Illumination studies, the vehicle's got to carry all of its own lighting because it's pitch black inside. Entry, as I mentioned, is a problem because the entry location is a 6-meter long pipe that's 100 millimeters internal diameter. It's about 4 inches. So you got to fit through a 4-inch pipe and go 6 meters down before you even get inside. So that in itself is a challenge. Now,
The illumination is for the inspector, not for the.
it's for the autonomy. So it's a visual inertial is what we're using for the autonomy. So yeah, it's all camera based. So obviously for a camera to work, it's got to be able to see. See if I can start this video again. So I wanted to show this video. It's one of our early demonstrations where this is a mock-up of the pedestal area where the client actually came in and just put in obstacles in front of our vehicle, in front of the path of the vehicle. And I like this video specifically because it shows it kind of, its purple path is the designed path, and the vehicle kind of making adjustments as it moves. I really like it as it turns because as it turns around this corner here, it initially wants to fly under the obstacles because of what it saw when it first came in. And as it turns, it gets a much better view of what's there, decides, hey, no, I'm going to go over, and flies over the obstacles. This is one of our more simple demonstrations, one of the early on ones, but I really like that one specifically because of what it shows. So I cannot talk about all the pieces to this because it was an enormous program, and we just don't have time to do that. So I picked out a couple of small pieces that I thought would be interesting. One is the radiation because it's kind of unique to this problem. And for us, we needed to use commercial off-the-shelf products. We weren't going to be designing everything from the ground up. We just didn't have time, and it's obviously very expensive to do that. So we really needed to use commercial off-the-shelf equipment. The question was, could commercial off-the-shelf equipment survive the environment that we were going to be operating in? Could it survive the radiation? Could it survive rain? All of those things. What degradation would we expect? Radiation causes degradation to your components. Sensors are going to have additional noise caused by the radiation. Can the sensors handle it? Can the autonomy algorithms handle the sensor radiation noise? And then lastly, do we actually present any additional safety concerns? If you know anything about small unmanned air vehicles, they use lithium polymer batteries. There was no literature that we could find that showed that lithium polymer batteries would survive or act well under heavy amounts of radiation. So we actually had to do that testing ourselves. So our experimentation was a little bit different than most radiation experimentation, where you usually put something in a hot cell, you expose it to a bunch of radiation, then you take it out and see if it still works. That really didn't interest us. Our interest was what was it going to do while it was being exposed to radiation, which meant building lots of test fixtures for testing components, for testing the entire system. Additionally, cesium-137 is actually the main source of gamma radiation at Fukushima Daiichi. The gold standard for testing, for radiation testing in hot cells is cobalt-60. The big question was, will cobalt-60 present the same types of radiation noise on the sensors as cesium-137? That was the big question TEPCO Holdings had. So we actually did a comparison study to verify that we were going to get the same kind of noise signatures. Lithium polymer batteries, we needed to test at high current draws, as you would see when the vehicle's flying. We also needed to test in that static after the flight state, because we never intended on recapturing these vehicles. They were going to go in and never come back out. So we needed to test in both of those states. And then obviously there was an enormous amount of component level and system level testing in hot cells. Oh, and to say, it did all survive all that. So it actually worked out really, really great. All of our components survived the expected flight times longer than the batteries, which was amazing and awesome. And there's an immense amount of more detail than that, but I, again, can't get into all that. Dripping water, I wanted to show a quick video of the dripping water test. We did conformal coding of the system. We actually use a Qualcomm Snapdragon flight board, which is what UPenn was using at the time, and we decided, hey, that's gonna fit in the pipe. It has a lot of the capabilities we need, let's use that. So we used a conformal coding process that we use for a lot of the NASA components that we build. And that worked out great. It's just coming up with, what do we coat? How do we coat it? What do you leave uncoated so that it can expel heat as needed? This is actually programmed to waypoint fly through, I did that, sorry. To waypoint fly through this streaming water. I know it's hard to see it hit it. I think on the second pass, you actually see the props, the water hitting the props, and it splashes. But this entire time during these flights, it's constantly being berated by water. And I will give it just a second as it comes around, and the light actually see the props, the water hitting the props. But yeah, it's constantly being berated by water. And all this is fully autonomous. This is all onboard lighting. This is one of our more recent tests. I mentioned getting into the primary containment vessel was a challenge. And like I said, that's because of that 4-inch pipe, or 4-inch inner diameter pipe that's down here. Obviously, flying through the pipe is not really a good idea. It's not practical. It doesn't really make sense. So it made more sense for us to deliver the vehicle and then let it fly from there. So we built a delivery system. The delivery system can obviously act as a comms relay point. It can provide additional light. It can provide additional cameras. But when we got to that, it was, okay, well, do we scale the vehicle we're using now? Because a lot of our original development was done on a UPenn vehicle that they had on hand and that we could just do development with. But do we take that vehicle and try to shrink it down and fit it through the pipe, or do we try to figure out how to collapse it? So we ended up going both directions. We tried both. Shrinking it down really didn't work. We shrunk it down to the point where it would fit in the pipe, but then we couldn't get the flight times we needed. It wasn't as stable as the larger vehicle. So we said, okay, we're gonna fold this vehicle. So this is the second prototype for the folding system, and it's the full Snapdragon flight complement. It's got 4 cameras on it. It's got 3 lights, the 2 here on the front, and there's one underneath that's got a really interesting lens on it to help disperse light consistently for the optic flow. Let me show you in the folded state. So this is our delivery system, prototype delivery system. This is the collapsed state of the system. Everything for basically collapsing the system is all done manually, and the delivery system holds it in place. And that's because we didn't want to add things to the vehicle. Anything we add to the vehicle, we got to carry, and that's just payload loss, that's loss of flight time. So the system retracts some arms that allow the vehicle to kind of spring into its flight frame. This is a better idea of the delivery system and kind of some of the components that are on the delivery system. Linear actuators, what we're using for kind of holding the vehicle in place. It's got cameras. It's got communication relay equipment. And this is actually a mock-up of kind of where we would be coming out at. We know that there's a conduit here that's going to be in the way. So we had to deal with all of that, make sure it would fit, it would deploy correctly. This is a video of us, and a much smaller pipe, obviously, doing some tests. This one's got all light because I wanted you to be able to see kind of the actual deployment of the vehicle. The right is in complete darkness. Both these do an autonomous takeoff, and then I do some I use the GUI interface to just give it waypoint commands to kind of come back over to the table. But you'll see this one pop open. It's basically spring-loaded. So there's a spring on the system. It pops into place. The arms lock in place using a flat spring. And as soon as that's ready, we confirm that on the other end via some of the cameras on the delivery system. We will unlatch the vehicle because we're actually holding it down to the delivery system just in case it rotates while it's in the pipe, it doesn't fall out. And then we do the autonomous takeoff. The one on the far right was the one that was most interesting to us because it was in the dark. We were going to have to deal with changes in shadows. We were going to have to deal with the over-contrast, the overexposure we were going to have when we initially took off, the reflections from the inside of the pipe, all of those things that we were going to be concerned about with the algorithm being able to handle the vehicle's takeoff. I just want to kind of acknowledge everybody. Lots of people worked on this project or this program. So I think thus far it's been something like 65 different people have worked on it. Our team members, the University of Pennsylvania, one of which has moved to NYU, have been awesome. They have great teammates. Tokyo Electric Power actually sent us a nuclear physicist to sit on site during the entirety of the program so that we didn't have to go through long communication turnarounds. We could just ask him constant questions about the site, about regulations, all of those kinds of things. And that's all I have for today.
We have time for maybe a question or two. Yeah.
Mauricio.
Richard, have you checked out the flyability drones and would they, is that sphere that they are,
The protective
the
sphere.
Yeah, have you tried that out? Because
We
tried those for inspecting engines and things like that at GE. I was wondering.
Right. So we did actually talk about those. It was the complexity of getting it through the pipe again. It was how do we compress that kind of protective sphere and get it into the pipe and then have it open up again. That became extremely complicated. So we did try a couple of different ways to kind of protect the props and things like that. On all cases, it affected the way the vehicle flew a little bit. In the end, we ended up just not using it. The vehicles just flew better without it. And we've done full test flights in our test fixtures to make sure that it can take off from that X-100B all the way into the pedestal and back out again and communicate all the data that it captured along the course of the mission. Please. This has not been deployed to Fukushima Daiichi. That is the goal of this, and that's what we work with TEPCO Holdings on. But we haven't actually scheduled a date for an investigation.
Okay, yeah, we'll get another chance to ask more questions. Let's
Thank you.
thank Richard again.